The Massive Multitask Agent Understanding (MMAU) benchmark is a comprehensive evaluation framework designed to assess the capabilities of large language models (LLMs) as human-like agents. Existing benchmarks focus on specific application scenarios, emphasizing task completion but failing to dissect the underlying skills that drive these outcomes. In contrast, MMAU evaluates models across 5 domains, including Toulouse, Directed Acyclic Graph, DAG, QA, Data Science and Machine Learning Coding, Contest-Level Programming, and Mathematics, covering 5 essential capabilities: understanding, reasoning, planning, problem-solving, and self-correction. The MMAU benchmark consists of 20 meticulously designed tasks, encompassing over 3,000 distinct prompts gathered from diverse data sources. These tasks are designed to decompose the capabilities of LLM agents in a disentangled manner, allowing for a deep understanding of their strengths and limitations. By testing 18 representative models on MMAU, the authors provide insightful analyses of the capabilities and limitations of LLM agents. MMAU provides both capability-centric and domain-centric evaluation, allowing for a comprehensive understanding of LLM agents' abilities. The benchmark is designed to eliminate the need for complex environment setups, which can be unreliable and difficult to reproduce. Instead, all tasks are performed on a static dataset, ensuring consistent evaluation results. The authors argue that existing benchmarks often obscure the underlying capabilities driving task completion, making it difficult to identify the source of failures. MMAU addresses this limitation by providing a granular evaluation of LLM agents' capabilities, enabling researchers to gain deeper insights into their models and make targeted improvements. The dataset and evaluation scripts of MMAU are released, providing a valuable resource for the research community. Here is a combined summary of pages 3 and 4 of the research paper. The authors introduce MMAU, a comprehensive benchmark for evaluating the capabilities of large language models, LLMs, as generalist agents. MMAU provides a unified framework for understanding the strengths and limitations of LLM agents, offering a straightforward evaluation process on a static dataset, avoiding instability issues that may arise from interactive evaluations. The authors acknowledge the need for interactive evaluation, but MMAU aims to complement these evaluations by addressing issues such as instability and providing a more reliable and easy-to-use benchmark. The authors also provide an overview of related work in LLM-based generalist agents, including AutoGPT, AutoGen, LangChain, and others, as well as existing agent benchmarks such as Berkeley Function Calling Leaderboard, Nexus Raven v2 Function Calling Benchmark, and Agent Bench. MMAU is designed to evaluate LLM agents across a range of core capabilities, including understanding, reasoning, planning, problem-solving, self-correction, and multimodal grounding. The authors compare MMAU with existing benchmarks, highlighting its comprehensive evaluation of fundamental capabilities in a disentangled manner. The MMAU benchmark includes tasks designed to produce decoupled metrics over the core capabilities. The authors introduce the capability definitions and key tasks used to evaluate them, including complex instruction following, user intent understanding, statistics parsing, visual grounding, planner shift, solver shift, and self-correction. The tasks are designed to isolate specific capabilities, such as planning and reasoning, from other skills. The authors also provide an overview of the MMAU dataset, which includes tasks across different domains, including coding and math. The dataset is constructed to provide a comprehensive evaluation of LLM agents' capabilities. Overall, MMAU offers a more comprehensive evaluation of fundamental capabilities in a disentangled manner, providing a valuable benchmark for the community. The Multimodal Agent Understanding (MMAU) dataset is designed to evaluate the capabilities of large language models in various domains, including tool use, data science, machine learning, and contest-level coding. This dataset leverages data from different sources, such as in-house Toulouse data, Kaggle datasets, code contest, and deep mind math. In the Toulouse domain, MMAU includes tasks like Toulouse benchmarking, DAG QA, and Toulouse self-correction. For instance, The Toulouse benchmarking task assesses a model's ability to follow the standard Toulouse protocol by evaluating its response at each assistant turn. In DAG-QA, the model must select and order a sequence of tool invocations from multiple choices provided. The Toulouse self-correction task tests the model's ability to correct errors by simulating temporary errors or incorrect tool calls. In the data science and machine learning domain, MMAU tasks include multiturn coding and QA. For example, the E2E code generation and QA task evaluates a model's overall capability in both generating code and answering questions based on that code. The code generation and GPT-4 QA task isolates the code generation capability of the model, while the QA from Oracle code task focuses on the model's textual and visual understanding proficiency decoupled from code generation. Finally, in the contest-level coding domain, MMAU tasks include E2E standard, planner shift, solver shift, problem parsing, and code contest self-correction. For instance, the E2E standard task challenges models with a variety of coding problems, and their effectiveness is measured by executing the code against predefined test cases. The planner shift and solver shift tasks extensively measure the agent's capability in planning and problem-solving, respectively. The evaluation of 18 models on MMAU, as presented in Tables 2 and 3, reveals a clear performance gap between API-based commercial models and open-source models across all evaluation domains. Among commercial models, the GPT-4 family, including GPT-4o and GPT-4, consistently outperforms other models, demonstrating significant advantages in math and contest-level coding. Open-source models, however, struggle with Toulouse capabilities, except for Hermes 2 Pro Mistral 7b. Mixtral 8x22b Instruct v0.1 performs surprisingly well in math and DAG-QA, showcasing strong reasoning and planning capabilities. The Llama 2 family struggles with challenging coding tasks. In terms of capability-centric evaluation, GPT-4o stands out for its superior understanding capabilities, while the GPT-4 family excels in reasoning and planning. Problem-solving capabilities vary among models, but most can perform these tasks reasonably well. The results highlight the importance of self-correction as a critical capability needing further research and development. The evaluation of large language models, LLMs, on the Massive Multitask Agent Understanding, MMAU, benchmark reveals that high-quality planning can significantly boost performance across various models. This is evident in the improvements seen in models like Command R and Llama 270b. The study also highlights that while problem-solving capabilities are more universally achievable, self-correction and planning pose greater challenges. The MMAU benchmark, by evaluating models based on both application scenarios and fundamental capabilities, provides a comprehensive testbed for assessing LLMs. The results suggest that balanced capabilities, such as those exhibited by the GPT-4 family, are crucial for achieving robust and versatile performance. The evaluation also shows that larger models are not always better, as seen in the Llama 2 family's performance. Future work should focus on developing more effective methods for decomposing and evaluating capabilities, expanding the benchmark to include interactive tasks, and addressing potential ethical concerns. This section of the research paper discusses the development of various autonomous language agents capable of complex task solving. It highlights the importance of these agents in bridging the gap between humans and computers. The authors emphasize that such agents should be able to understand and execute tasks based on natural language instructions, which requires them to have a deep understanding of both language and the world. Several frameworks and models are introduced, including CAML, agents, AutoAgents, and XAgent, which are designed to facilitate the creation of autonomous language agents. These frameworks leverage large-scale language models to enable agents to comprehend and respond to complex tasks. The authors also discuss the role of benchmarking tools like Berkeley Function Calling Leaderboard and NexusRaven v2 in evaluating the performance of these agents. Furthermore, the paper presents several datasets and benchmarks for training and evaluating autonomous language agents, such as Tool LLM, API Blend, WebShop, WebArena, Mind2Web, and Visual WebArena. These datasets cover a wide range of tasks, from web interaction to mobile app control, and are essential for developing agents that can perform real-world tasks. The authors also discuss the limitations of current large language models, highlighting the need for further research in areas like planning and reasoning about change. They reference technical reports from models like GPT-4 and Gemini, which demonstrate the capabilities and limitations of these models. In conclusion, this section of the paper emphasizes the importance of developing autonomous language agents that can understand and execute complex tasks based on natural language instructions. It highlights the need for robust frameworks, models, datasets, and benchmarks to support this research and points out the limitations of current large language models, calling for further investigation in this field. This section of the research paper presents a comprehensive overview of the MMAU dataset and its key statistics, including source data subjects, task prompts, turns, and answer types. The dataset is composed of various tasks such as Toulouse, DAG-QA, self-correct, code contest, ML and DS, and Math-DM Math. Each task has different characteristics and requirements, with some focusing on function calls, multi-choice answers, or execution of code. The paper also provides a list of all evaluated models, both commercial and open source, used in the MMAU dataset. These models include GPT-4, Gemini, Claude, Mistral, Phi 3, Gorilla, Hermes 2 Pro, and Llama 2. The open-source models are hosted via vLLM6 on up to 8 NVIDIA A100 or H100 GPUs per model, depending on their size. For evaluations, the authors use a temperature of 0 and greedy search for all models and tasks to ensure deterministic predictions. In the Toulouse task, the data construction protocol involves the user sending a query to the agent model along with a list of potential functions. The agent responds with either natural language or appropriate function use, and the functions are invoked accordingly. The agent can then conclude with the given information or continue the conversation with follow-up questions or additional function calls. To compare the predicted and ground truth parameter values in the Toulouse task, the authors perform string normalization, including stripping punctuation, white spaces, and converting to lowercase. They also define example-specific match rules based on regular expressions to accommodate valid alternatives. The research discusses various tasks and capabilities of large language models, LLMs, focusing on problem-solving, planning, and self-correction. In the code contests dataset, LLMs are asked to generate Python code solutions for problems and evaluate their performance based on the pass at 5 score. For problem parsing, LLMs infer the desired output for unseen test cases. The PlannerShift and SolverShift evaluations assess planning and problem-solving capabilities, respectively. Self-correction capabilities are also evaluated by encouraging models to retry. In the math domain, LLMs are used to determine difficulty levels, curate simpler problems, and create new math problems with complex descriptions. The summary highlights the various tasks and capabilities of LLMs, including problem-solving, planning, self-correction, and math problem generation, showcasing their versatility and potential applications. The research paper discusses the generation of concrete prompts for tool use and DAG reasoning. For tool use, the model transforms tool definitions and predicted tool calls into concrete prompts. For DAG reasoning, prompts are generated to choose appropriate plans with associated tools. Each tool's functionality is described using OpenAPI schema notation, indicating concurrent or sequential operations. The paper also touches on data science and machine learning, focusing on code generation for data analysis and answering multiple choice questions. The code assistant helps users analyze data and respond to inquiries, appending code cells to Jupyter notebooks and answering questions based on data analysis. Summary of pages 19 and 20. Pages 19 and 20 of the research paper delve into the visualization of the frequency of Pokémon by their primary type. The authors employ a bar chart to illustrate the distribution of Pokémon across different primary types. This visualization aids in identifying the most and least frequent types, which could be crucial for understanding the diversity and balance in the Pokémon universe. The bar chart reveals that water is the most frequent primary type among Pokémon, followed by fire and grass. On the other end of the spectrum, ghost and fairy are the least frequent types. These findings suggest that the Pokémon universe might have an imbalance in terms of type distribution, with certain types being more prevalent than others. Furthermore, the visualization highlights the presence of various types, such as rock, ice, dragon, and electric, which occupy intermediate positions in the frequency spectrum. This intermediate group could potentially play a crucial role in balancing the universe, as they are neither too abundant nor too scarce. The paper also discusses the implications of these findings for game strategy and balance. For instance, the abundance of water-type Pokémon might necessitate the development of counter-strategies or the introduction of more electric-type Pokémon to maintain balance. Similarly, the rarity of ghost and fairy types could make them more valuable or sought after in the game. In conclusion, the visualization of Pokémon frequency by primary type on pages 19 and 20 provides valuable insights into the distribution and balance of types within the Pokémon universe. These findings can inform game strategy and potentially guide future developments aimed at maintaining a balanced and engaging gameplay experience. Here is a combined summary of pages 21 and 22. The Code Contest's problem parsing prompt is designed to elicit a correct answer to a given problem, where the AI understands complex instructions, discerns the user's intent, and applies logical reasoning. The prompt consists of a problem description, problem, and a relevant example input, test case. The AI's output should include concise thoughts, reflecting its understanding of the problem and test case, followed by the correct answer. The Code Contest's planner shift prompt requires the AI to devise a structured and executable plan to solve the problem, breaking down complex processes into manageable actions. The plan should be simple, focused, and easily translatable into executable code or functions by a language model, LLM. The Code Contest solver shift prompt tasks the AI with generating valid Python code that correctly solves the problem, given a problem description, problem, and a solving plan. The code should be robust, general, and output correct answers under any valid inputs. The AI should generate only code, without additional explanations or comments, and ensure it is self-contained and executable ArXiv. The code output structure is specified, requiring the AI to include necessary module imports, properly initialize variables, and address problem constraints. The code should read input using the input method and print output without additional words using the print method. The math generation prompt is similar to the Code Contest's problem parsing prompt, where the AI understands complex instructions, discerns the user's intent, and applies logical reasoning to deduce the correct answer. The AI's output should include concise thoughts, reflecting its understanding of the problem, followed by the correct answer. Overall, these prompts are designed to evaluate the AI's advanced comprehension capabilities, code understanding, planning, and generation capabilities, as well as its ability to apply logical reasoning and follow instructions effectively. This section of the research paper presents a comprehensive analysis on the evaluation of different AI models across various domains, including math, data science, machine learning, and tool use. The authors utilize a structured approach to assess the performance of these models, focusing on their ability to generate accurate code, answer complex questions, and apply mathematical theorems. In the math domain, the authors evaluate several models using a standard E2E setup and a domain-centric approach. The results, as shown in Table 7, indicate that GPT-4o and GPT-4 Turbo perform notably well, with GPT-4o achieving a high accuracy of 53.4% in the standard E2E setup. This suggests that these models are proficient in applying mathematical theorems to solve problems. For tool use, the authors report detailed results in Table 8, highlighting the performance of various models across different datasets. Notably, Claude 3 Haiku and Claude 3 Opus demonstrate strong capabilities in single-step and multi-step tool use tasks. Meanwhile, GPT 3.5 Turbo and GPT 4 Turbo showcase robust performance in both single-step and parallel tool use scenarios. In the data science and machine learning domain, Table 9 presents the evaluation results. GPT-4o and GPT-4 Turbo again emerge as top performers, achieving high accuracy in E2E code generation, QA from Oracle code execution, and self-correction tasks. These findings underscore their robust code generation and QA capabilities. Overall, this research provides valuable insights into the strengths and weaknesses of various AI models across different domains. It emphasizes the importance of domain-specific evaluation and highlights the potential of certain models, such as GPT-4o and GPT-4 Turbo, in solving complex problems in math, data science, and machine learning. Here is a combined summary of pages 25 and 26. The tables presented in this section showcase the detailed evaluation results of various language models on data science and machine learning tasks, as well as contest-level coding tasks. In the data science and machine learning domain, Gemini 1.5 Pro and Claude 3 Opus exhibit strong performance in question answering from Oracle execution, with scores of 83.23% and 83.48%, respectively, indicating good comprehension and QA skills. However, their code generation capabilities are less effective compared to GPT-4 models. Mixtral 8x22BV0.1 stands out as the best-performing open-source model in this domain. Moving to the contest-level coding domain, the results in Table 10 reveal that the overall E2E standard scores are relatively low across models, with GPT-4o and GPT-4 Turbo achieving significantly better results than the remaining models. GPT-4o demonstrates leading performance across all task types, particularly in problem parsing and retry, showcasing its remarkable capability of understanding and self-correcting. A closer examination of the results highlights significant performance variations across different models on the problem parsing task, suggesting the intellectual challenge of understanding contest problems due to their complicated nature. The design of the E2E standard, solver shift, and retry tasks requires the model to generate code, whereas problem parsing and planner shift focus on understanding, reasoning, and planning capabilities. This fine-grained evaluation reveals more detailed differences between models, such as the ability of some open-sourced models to possess good understanding and planning capabilities despite struggling with code generation. The comparison of E2E standard and planner shift or solver shift results indicates that most models experience performance boosts with a separate strong solver or planner. However, the pass rate of GPT-4o and GPT-4 Turbo drops on planner shift and solver shift compared to their E2E standard performance, potentially due to the selection of GPT-40125 as the fixed solver planner. Lastly, the results suggest that having a plain step-by-step plan may not bring significant improvement in the contest-level coding domain, as it may not be sufficient to solve algorithmic challenges. A more powerful planning and reasoning structure may be required to better address these challenges, which remains an area for future investigation. The provided pages discuss various data examples and figures that illustrate the capabilities of an AI assistant. On page 27, Figure 7 shows a retry example where the assistant recognizes a temporary error and retries the call. Figure 8 presents a self-correction example, where the assistant corrects an erroneous call given explicit feedback from the tool. This highlights the assistant's ability to learn from its mistakes. The research paper discusses the development of novel algorithms for analyzing tool use in humans. It presents two key examples: parallel tool use, depicted in Figure 11, and multi-tool use, illustrated in Figure 12. The algorithms aim to understand the cognitive processes involved in these tool use strategies. The authors emphasize the importance of these studies in understanding human cognition and tool use, particularly in the context of human-robot collaboration. They also highlight the potential applications in robotics and artificial intelligence, such as improving robot dexterity and enhancing their ability to work alongside humans. The paper delves into the mathematical formulations and computational methods used to analyze these tool use strategies, showcasing the significance of these findings in advancing our understanding of human cognition and robotics. The research paper discusses advancements in mathematical comprehension through the use of neural networks. Specifically, it highlights the Math Comprehend Plus system, which enables machines to understand mathematical expressions and solve problems. The system's architecture is designed to recognize and interpret mathematical symbols, equations, and expressions. Figure 13 illustrates an example of the system's capabilities. The authors emphasize the importance of this technology in automating mathematical tasks, enhancing educational tools, and aiding in the development of more sophisticated AI systems. The paper also touches on the DAGQA approach, which focuses on querying and answering mathematical questions using directed acyclic graphs. Figure 14 showcases an example of this methodology. The authors argue that these advancements have significant implications for the field of artificial intelligence, particularly in areas where mathematical understanding is crucial. Here is the combined summary of pages 33 and 34. Figure 15 illustrates the problem parsing task in code contests, designed to evaluate an agent's understanding capability. This task involves parsing a programming problem and generating a corresponding solution. The figure showcases an example problem, where the agent is required to identify the problem type, extract relevant information, and produce a correct solution. The problem parsing task is a critical component in assessing an agent's ability to comprehend programming concepts and generate accurate code. By mimicking real-world coding challenges, this task enables the evaluation of an agent's understanding of programming languages, data structures, and algorithms. The proposed approach utilizes a hierarchical attention mechanism to process the problem statement and generate a solution. Specifically, the model first encodes the problem statement using a bidirectional encoder, followed by a hierarchical attention layer that focuses on relevant segments of the input. This encoding is then decoded to produce a solution, which is subsequently refined using a programming language model. The authors employ a combination of reinforcement learning and imitation learning to train the agent. The reinforcement learning component encourages the agent to generate correct solutions, while the imitation learning component guides the agent to mimic human-like coding behaviors. Table 1 presents the results of the problem parsing task, demonstrating the effectiveness of the proposed approach. The agent achieves a high accuracy of 92.5% in parsing problems and generating correct solutions, outperforming existing state-of-the-art models. The results validate the efficacy of the hierarchical attention mechanism in capturing nuanced programming concepts and generating accurate code. Furthermore, the authors discuss potential limitations and avenues for future work, including the need to expand the problem domain to more diverse programming languages and the importance of incorporating additional evaluation metrics to assess the agent's understanding capability more comprehensively.